Okay, so this table is describing a soccer ball's height above the ground after it's kicked. And we're going to be graphing this. So how would you set up the graph? Would time be the x or y axis? Good. Okay, this is our independent variable. So we're looking at, over time, the height of the ball. Would the ball start at 0, 0? Would it start on the ground? Because the question says it starts in the air, maybe it was a drop kick. Where does the ball get kicked from? How high off the ground? 0.10 meters. So you guys are actually going to create a graph. Okay, so we know that it cannot start here. And we're going to be looking at the time and the height of the ball. Okay? Okay, so we're looking at the ball starting from 0 seconds. It hasn't been kicked. Up until how long? How long is the ball in the air for? So from 0 to 3 seconds. And the height, what's the highest height that this ball goes? This is the highest height it's going to go. So you need to have a scale that goes from 0 to, let's say, 14 or 15, okay? You decide what scale you want to use. And we have y is the height, okay? So you need to come up with a scale for both x and y axis. Okay, so when you graph it, it should look something like this. The textbook used a scale of 0.5 for the x-axis, and they counted by 4s for every 2 squares for the y-axis. Okay? What can you tell me about the shape of the graph? How do you know it's a parabola? It's a symmetrical curve, okay? Which means that if I divide this in half, which is somewhere around here, both sides are exactly the same. They're identical, right? You can tell me from the graph, can you see where the maximum height of the ball was? How high did this ball go? And if we look right here, the highest point of this parabola is, now it's really hard to tell in here, but looking back at the table, we know that the maximum y value, right, this is our y value, is 13.8. That means the ball did not exceed 13.8 meters. That was the highest point it got. How many seconds was the ball in the air altogether? So from the starting, this is where it was kicked, and it got kicked, and then eventually it landed. Looking at the table, the last point they give you is 3 seconds, and it's 4 meters. So at 3 seconds, the ball is still in the air. When does it hit the ground? Right here, which is what? Just as an estimate, probably around 3.2 to 3.3 seconds, okay? Looking at the graph. That's how long it's in the air for. It hits the ground at this point, right? That's the ground. The x-axis is the ground. How long did it take, so how many seconds did it take for the ball to hit the highest point? How many seconds passed when it got to its highest point? 1 point. Okay, we can look back at the table to see. This was the highest point, so we know that's got to be the vertex, right? The highest point is where the vertex is, and it took 1.5 seconds for the ball to get to the highest point. Okay, so I just used the word vertex. What is a vertex of a parabola? So basically, the vertex is the point where the parabola changes direction. So in this parabola, it increases, and then all of a sudden here, it changes direction and it decreases. So the vertex is also the highest point of the parabola, or if the parabola opened this way, what would it be? The lowest point, which is the minimum value. Okay, so in this last example, again, we're looking at a table of values. We're given the values of x and y. We're going to figure out if this is linear or quadratic. So let's figure out the first differences. Does everyone remember how to figure out the first differences? Okay, so what do? What am I subtracting? Good. 6 take away 1 equals Then I'm going to subtract 9, take away 6. So just by calculating the first differences, we see that they are 5, 3, 1, -1, -3, -5. Can this possibly be linear? No. First differences are not the same. So we know it's non-linear, right? But we have to see if it's quadratic. Something can be non-linear and still not be quadratic, right? For example, if I draw this, look here. Is that linear? Is that quadratic? No, that's not quadratic. We have to see if this is quadratic. So we're going to find the second differences. So same thing. 3 take away 5 equals -2. 1 take away 3 equals. Once we find all the second differences, they are all the same. So if the second differences are the same, what does it tell us about this relation? Quadratic. It must be quadratic if the second differences are all the same. Okay, so the third way you can tell if it's linear or quadratic is by looking at the equation. You guys told me earlier, what is the form of a linear equation? Y equals mx plus b. What is the form of a quadratic relation? Ax squared plus bx. What do you notice about the linear equation that's different from the quadratic equation? If you notice, a quadratic relation must have to the power of 2. It has to have a square. Linear is to the power of 1. You can imagine there's a 1 there. Okay, so just by looking at the equations then, A, linear or quadratic?
Linear.
B, C, D. What about this one? Linear or quadratic? Neither. Thank you. Because it doesn't have power of 1 or power of 2. Okay, so in summary, how can you tell by looking at a graph if it's quadratic? What does it have to look like? Yeah, if it's a parabola, so if it's symmetrical, oops, that's not very symmetrical. Okay. How can you tell from a table if it's quadratic? If the second differences are the same, and how can you tell from an equation if it's quadratic? If it has an x squared term. Okay, so that's what you need to.
Made with Doodlecast Pro.